Boolean algebra is the main driver for how we look at logic in electrical engineering. Now recall from the previous video where we looked at three kind of gates, which are the building blocks for all of the logic that we're going to concern ourselves with, where we had an AND gate, an OR gate, and a NOT gate, where we had inputs on the left and outputs on the right. Now what we want to look at for all of these gates and all combination of gates is how can we express this output as some function of A, B, and however many inputs there are. And to do that, we introduce Boolean algebra. So with Boolean algebra, we're going to concern ourselves with everything inside the brackets here. So we have a plus sign, a multiplication sign, 0 to 1, which would be our low and highs. We have parentheses. For the sake of this set, we have an input A, and we have the inverse of A, denoted by A bar. And there's a few rules or properties that we want to look at for Boolean algebra, and they're given in two forms, which are the AND form and the OR form. First is the commutative property, where we have A multiplied by B is equal to B multiplied by A, and sometimes you'll see this dot here to represent the multiplication sign, sometimes you won't. We also have associative properties, where we can simply group things by parentheses. We have distributive properties, where in this case we would have A multiplied by B plus C in parentheses, and we simply distribute A to B and then A to C to have AB plus AC. We also have the complement rule, where you would have A multiplied by the inverse of A equal to 0, or you would have A plus A inverse equal to 1. Now, one of the main drivers for logic is De Morgan's law. We'll look into proving those in a little bit, as they seem a little bit confusing when you first look at them. We also have the identity property, where A, or any input, times 1 is equal to A. Or you can have 0 plus A is equal to A. You have the null property, where you have A times 0 is equal to 0, or you can have 1 plus A is equal to 1. And then this last rule, which is a little bit confusing if you relate it to conventional mathematics that we're used to, where you have A times A equal to A, or you can have A plus A equal to A. So from this, we can go back up to our original gates. And for the AND gate, we could express that as F being equal to A times B. For the OR gate, F would be equal to A plus B. And for the NOT gate, F would be equal to the inverse of A, or A bar. So now we're going to look at actually proving De Morgan's law, one of the forms where we had the expression given as this term here. So what we can do is simply just write out our inputs A and B and have all the combinations. And then we can take that left-hand side of the equation, put it here, and the right-hand side of the equation and put it here. And all we're going to do is compare the values. So when A and B are both 0, you would have 0 plus 0, which is going to be equal to 0, but the inverse of 0 is 1. So that's how we get that 1 there. Now simply when A or B, or the combination of A and B, are equal to 1, the sum of A and B will also be equal to 1. And the inverse of that is equal to 0 for these three cases. Now looking at the right-hand side, when A and B are 0, you would have the inverse of 0 times the inverse of 0, or 1 times 1, which is equal to 1. In any case where A or B are high, the inverses would be 0, and you would have 0 times some value, which is equal to 0. But what we want to look at is an example where we expand some function f, given by this term here. Now we switch the inputs from A and B to x, y, and we also brought in z. What we're going to do here is simply make a substitution and say that xy is equal to A, and x bar z is equal to B. So we can simply write that function equal to A plus B, and then we have the inverse, and we can use the De Morgan property such that this is equal to A inverse times b inverse, which is equal to x, y inverse times x bar z inverse. So from this term here, we're also going to use De Morgan's law again. And now we're going to say that this term here on the left is equal to x inverse plus y inverse times x plus z inverse. And this is where we seemingly may get stuck because we're not sure what to do in terms of Boolean algebra. But now we're going to go back up to the distributive law and look at this right-hand side equation. So we can make a little side note here. Say that a plus b times a plus c. I'm going to question that is equal to a plus b times c. So conventionally in algebra, you might try to use a FOIL approach, and let's see how that works. So our first terms would simply be a times a plus our outside terms plus our inside terms, BA, then our last terms, BC. So we know from this property here that this is going to be equal to A plus AC plus AB, where here we simply used the commutative property plus BC. And now what we're going to do, simply factor things out. Again, using the distributive property. And we're going to call this A times 1 plus C plus B plus BC. And from this, you can see that 1 plus A, or 1 plus any input, is equal to 1. So this term here is equal to 1. And what we get is A plus BC. And looking up here, we can see that those terms match. So coming back to this term here, we can first expand our terms. So we get x bar x plus x bar z bar plus y bar x plus y bar z bar. That's what f is going to be equal to. Again, we can look at this right here, and this is going to be equal to 0. So f is simply equal to x bar z bar plus y x plus y bar z bar. And that is how we can expand our original function.